Hello students, this is Mr. Gomez, Chemistry. We're going to go ahead and get started with today's lesson on metallic bonding and properties. This is just an announcement for you students. There's going to be a test on Wednesday for A-Day students and a test on Friday for B-Day students. So go ahead and look at what will be on that test and then prepare, okay? So, once again, today's lesson is going to be on metallic bonding and properties. So what is your learning goal? Your learning goal is I can describe metallic bonding and explain metallic properties such as thermal and electrical conductivity, malleability, and ductility. Here is the success criteria. So, by the end of today's lesson, you should be able to understand the nature of metallic bonds, understand the sea of electrons, understand why metals are good conductors of heat and electricity, understand why metals are malleable, and understand why metals are ductile. So, what I'd like to do is I'd like to go over some bonding, okay? In order for us to understand metallic bonding, let's go ahead and review ionic and covalent bonding. So, let's talk about ionic bonding. Ionic bonding occurs when valence electrons are transferred between a metal and a nonmetal. So, in ionic bonding, valence electrons are lost or gained. As a result of this, ions, which are positively or negatively charged atoms, these are created by the loss or gain of electrons, and the resulting ions are electrostatically attracted to each other. So if you look at this visual example, we have NaCl, sodium chloride, otherwise known as table salt. This is the quintessential example of an ionic bond, okay? So, in this situation, sodium will lose its valence electron. It will no longer have it. Chlorine will steal that electron away. So, as a result, on the right-hand side, sodium, which has lost an electron, now becomes a positive ion. Chlorine becomes a negative ion. Those two ions are electrostatically attracted to each other, and so they will bond. Okay, that's a review about ionic bonding. Covalent bonding. This occurs when valence electrons are shared between two nonmetals. So in covalent bonding, none of the atoms has enough strength to actually steal the electron away from the other. So end up sharing valence electrons, okay? And something else to remember is covalent bonding is between two nonmetals, okay? Whereas ionic bonding was between a metal and a nonmetal. In covalent bonding, these shared electrons help each atom fulfill the octet rule. Remember that the octet rule is the rule that all atoms, except for hydrogen, want to have 8 electrons in their outer shell. And hydrogen is the exception because it only wants 2 valence electrons. That's because hydrogen is in the first period of the periodic table and only has one energy level. That first energy level holds the 1s orbital and can only hold 2 valence electrons. That's why hydrogen only wants 2 valence electrons to be happy. All right, so it's very important for you to understand which elements are metals and which elements are non-metals on the periodic table. Your periodic table, the one that you're going to be able to use on my exams and on the district exams, if you look at this periodic table, you should be able to see a thick line. So if you look at boron, to the left of boron, on the left-hand side of boron's box, underneath boron, you're going to see a thick line that goes down from boron all the way to astatine, okay? It looks like steps that are going down, okay? So if you look at that thick line, everything to the right of that line are the nonmetals. And everything to the left of that line are the metals of the periodic table. Also remember that hydrogen is a non-metal. Don't get confused that because hydrogen is on the left-hand side, that it's a metal. It is a non-metal, okay? And why is this important? This is extremely important because when you're looking at bonding, you have to understand that if you see a metal and a non-metal, it's an ionic bond. If you see two non-metals bonded, they're covalently bonded. So there are way different types of implications depending on the types of atoms that are bonded together. So we've just reviewed ionic bonding, non-metal and a metal. We've also reviewed covalent bonding, two non-metals. Well, what happens when you have two atoms of metals that are bonded together? This is where we get into metallic bonding, and this is the lesson for today's class. So, what is metallic bonding? Let's read the definition. There are a number of different definitions that could be said for any number of things, but this is the definition that we're going to go with today. Metallic bonding is the force of attraction between metal atoms and the sea of electrons. So, this may not make sense to you right now, but I want you to look at this picture on your screen on the right-hand side. So here we have a metallic bond, and it says that it's an electrostatic attraction between electrons and metal ions. So try to keep that in mind. And you might be able to go back at the end of this lesson, refer back to this image, and be able to say, I finally understand it. So hopefully that will be the case. Because remember, one of your learning objectives is to be able to understand the nature of metallic bonding. So let's talk about metals and their valence electrons. Metals tend to lose their valence electrons. Remember, valence electrons are the electrons that are found in the outer energy level of an atom. When we talk about metals, generally, metals tend to lose their valence electrons in order to become stable and have a full valence shell underneath. Cations, or positively charged atoms, are formed as a result. So let's take a look at this image right here. We're looking at a magnesium atom. Magnesium is a metal. If you go to the periodic table, you'll see that it's on the left-hand side of that thick line that I talked about. And so, once again, metals tend to lose their valence electrons. Remember that the octet rule states that all atoms, except for hydrogen, want 8 valence electrons in their outer shell. For whatever reason, there actually is a reason, but the explanation can be a little long. So you're just going to have to take my word for it that metals tend to get rid of their electrons, okay? Their valence electrons. So if you look at this screen on the left-hand side, magnesium has 2 valence electrons because it's in group 2 or the second column of the periodic table. Magnesium is going to lose these 2 valence electrons. Okay? So what's going to happen as a result? The result is that magnesium atom is going to become a positively charged ion. So it's going to become +2. Because since it lost 2 electrons, it's going to have a +2 charge on it, okay? If you lose electrons, because electrons are negatively charged, you become more positive. That's why if you look on the right-hand side, you see these little purple-colored magnesium atoms. They've lost their 2 electrons, so now they're a positively charged ion with a charge of +2, okay? So here are the resulting positive magnesium 2+ ions. So the question becomes, what happens to those 2 valence electrons that the magnesium atom lost? A sea of electrons is formed. So the lost valence electrons will surround the newly formed cations, or positively charged atoms, in a sea of electrons. So if we have a piece of magnesium, okay, we're holding magnesium in our hand, hopefully with gloves to be safe. Anytime you're working with elements and chemicals, you have to be careful, okay? But let's say, for example, we have an amount of magnesium, okay? So we have this is a look into these atoms, okay? All of these magnesium atoms have lost 2 valence electrons in order to have a full valence shell underneath. These electrons that they lost will end up surrounding these magnesium cations, almost in a sea of electrons. That's why we call it the sea of electrons. So if we look at the right-hand side, this is kind of a visual, animated representation of the sea of electrons. So you see the magnesium cations, and you also see these electrons kind of floating around, okay? That's what we mean when we call this the sea of electrons. And the sea of electrons is very important to metallic bonding because it also explains the numerous unique properties that metals have. So, what I'd like for you to do right now is on your worksheet, you're essentially going to design what you see on the right-hand side. Magnesium cations in a sea of electrons. So on your worksheet, design a metallic bonding model for 9 atoms of magnesium. Correctly label each magnesium cation with its correct charge. Surround the 9 magnesium atoms in a sea of electrons with the correct number of valence electrons that would exist if 9 magnesium atoms lost their valence electrons. So what I'd like for you to do right now is to go ahead and pause the video and then take your time, take 5 minutes, or because you're doing this at home, take as much time as you need to design this model. Remember, it's very important to understand the charges of these magnesium atoms once they lose their valence electrons. And it's very important for you to understand how many valence electrons would be floating around in this sea if 9 magnesium atoms lost their valence electrons. So please, pause this video and then get to work. Okay, so now let's do a little bit of check for understanding, okay? Let's see your progress. So try not to look at any notes or anything besides what you have stored in your mind. So here's the first question. The attractive force between atoms in the sea of electrons is known as what? Okay. The attractive force between atoms and the sea of electrons is known as, the answer is C, metallic bonding. Next question. Let's see what you remember. Metals tend to do what? Try your best, give an answer, and we'll talk about it. Okay, metals tend to do what? The answer is B, lose electrons. Next question. A metal that loses electrons becomes what? Good luck. Okay, a metal that loses electrons becomes, the answer is D, a cation. The definition of a cation is a positively charged atom. So if an atom, a neutrally charged atom that loses electrons, becomes more positive and therefore a cation. One of the interesting ways that a lot of people remember cation versus anion, cation is positive because cats have paws. Okay? Maybe that will help you. We have another question. Metal atoms that lose electrons become surrounded by what? Let's see if you can remember this. Okay, metal atoms that lose electrons become surrounded by, the answer is C, a sea of electrons. So, let's talk about these valence electrons, okay? It's important to understand the difference between the valence electrons in metallic bonding versus those in ionic and covalent bonds, okay? Valence electrons in metallic bonds are free. Unlike ionic and covalent bonding, valence electrons in metallic bonding are not bound between two atoms. They are free, mobile, and delocalized. Those three words are very important when we're talking about the valence electrons in metallic bonding. Once again, free, mobile, and delocalized, okay? This means that they can move anywhere in the sea of electrons, okay? So let's take a look at this visual representation. Let's just, for example, say that this is a sample of, I don't know, an aluminum piece of metal, okay? So here you have those positive signs are the positive metal aluminum cations, okay? The lost valence electrons. Aluminum has 3 valence electrons. So all of those electrons, those valence electrons that have been lost from all of those aluminum atoms, they are free, mobile, and delocalized. They can move anywhere in this sea of electrons, okay? So they're not bound by the aluminum atom that they're closer to. They can actually move around, and if one electron goes away, another one steps in to take its place. So look at that image on the bottom to hopefully kind of see how this sea of electrons, the nature of the sea of electrons, okay? I was thinking the other day, how could we kind of sort of compare this to? Have you ever been to a bouncy house as a child? Or have you ever been to one recently to go with your baby brother, sister, or cousin at a birthday party, okay? You know those bouncy ball jumping places where you can just jump into a sea of bouncy balls? That's kind of sort of what I'm talking about. So when you jump into a huge pile of bouncy balls, you're free to move anywhere, right? And as you move, bouncy balls just fill in the place of other bouncy balls that have been moved around, okay? I don't know if that's the perfect analogy, but that's kind of where I'm going at with the sea of electrons. So, here's a video on metallic bonds and hopefully it can better help you to understand the nature of metallic bonding.
Metal atoms have few electrons in their valence shell, and these are relatively weakly held. Though metal atoms group together in a crystalline lattice structure, they have very different properties to the ionic solids. For example, solid metals are able to conduct electricity. This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom. Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations. The structure is held together by the strong electrostatic force between the sea of valence electrons and the metal cations. This is called metallic bonding. The electrons are constantly on the move, so the bonding acts in all directions. Metallic bonding is powerful enough to overcome the force of repulsion between the closely packed cations. The high melting points of most metals indicates the strength of the metallic bond.
Okay, so hopefully you got something out of this video. I would also say that there's an unlimited amount of videos on YouTube and resources on the internet. If you're still having trouble understanding the nature of metallic bonding, if you're still having trouble understanding the sea of electrons and how the sea of electrons are formed, okay? Also, don't hesitate to ask me as well. So let's go ahead and move on. So let's talk about metallic properties. The highly mobile sea of electrons is responsible for the unique properties of metals, such as thermal conductivity, electrical conductivity, malleability, and ductility. So, if you go back to your learning goals actually, your learning goal is to be able to understand why metals are good at heat conductivity, electrical conductivity, malleability, and ductility. So you should be able to explain why metals have the unique properties, these 4 unique properties. And you should be able to understand and explain why. Okay? Let's talk about thermal or heat conductivity. Metals are good conductors of heat because the sea of electrons are free to absorb heat energy, vibrate, and increase the kinetic energy. So let's take a look at this image here on the right-hand side. Let's say, for example, this is a piece of gold metal, okay? As you add heat to the gold metal, you can see that the sea of electrons are able to absorb that heat energy, vibrate, and move around. You'll learn later on in chemistry that temperature is just really the average kinetic energy of all the particles that are moving around in a substance, okay? So, as you apply heat energy to this piece of gold metal, the electrons are, as they absorb the heat, they move faster and faster and faster because the temperature is increasing. The sea of electrons allow this to happen, okay? That is why when you cook, you don't use a plastic pan, okay? People would think that you're crazy. Not only would it melt and then you have a bigger mess on your hands, but plastic is not a good conductor of electricity. We use metals because they are able to absorb heat energy and increase in kinetic energy as that heat is being applied to the metal, okay? This is an example of you've known chemistry all your life. You just haven't put it together in terms of being able to explain it in a chemical or scientific way. Hopefully today you can as well. So let's move on. Metals are also good conductors of electricity because the sea of electrons allow electricity to freely enter and pass through the metal. So what is electricity? Electricity is essentially the flow of electrons. And so this is absolutely perfect for metals, okay? Because if you look at the bottom, you see an image of electricity flowing through a metal, okay? Not only that, we're able to see the structure of metals. We're able to see the metal atoms in the sea of electrons that surround the cations, okay? So when electrical current or just a big bunch of electrons enter into the metal, they're able to freely enter and pass easily due to the sea of electrons. And so you've known all your life, or pretty much for a while now, that you should not hold a fork and then put it into an electrical outlet. You would not get a quarter and stick it into there, okay? That's because we know that metals can conduct electricity, but now you're able to chemically and scientifically explain why, okay? This is just a fun list of the most conductive elements in the universe, okay? So if you're looking at your periodic table, this is a list of the top 10 most conductive elements, okay? And they're metals. Silver has the highest electrical conductivity of all the elements on the periodic table. So I'll let you look at this list and hopefully you're able to add some more knowledge to your life, okay? Particularly pay attention to number 2, copper. Copper is a good conductor of electricity, and most of our wiring includes copper, okay? So when you plug in your computer laptop charger or you plug in your cell phone charger, the element that's most likely in those wires is copper, okay? So chemistry has very real life application, okay? We discovered these properties of metal, and as a result, we're able to improve our lives, charge our electrical items, and move about our business, okay? Now, let's talk about malleability. It's very important for you to understand the definition of malleability. It is the ability to hammer into sheets, or the ability to hammer a substance into sheets, okay? Metals are malleable. We're able to hammer them into sheets. That is because when struck by a hammer, the sea of electrons allow metallic atoms to slide past each other without breaking. Okay, so if you look at this image on the right-hand side, you see somebody hammering, and we can say a piece of gold, okay? So instead of breaking like it would in ionic bonds, because they're bound to only each individual atom, okay? The sea of electrons allows these metallic atoms to slide past each other, almost kind of like a gluey substance, okay? So here are some examples of malleability of metals, okay? So the quintessential example is aluminum foil, okay? Aluminum is a metal, but because it's malleable, because of its sea of electrons, we're able to hammer or press aluminum into these really thin aluminum foil sheets. And most of us use these almost every week when we have leftover food or we go to a barbecue. We'll typically wrap it up in aluminum foil for 2 reasons. One, because aluminum is malleable and it produces these nice convenient sheets, but also aluminum is a good conductor of electricity, okay? A conductor of heat, okay? We also see on the bottom an example of gold foil sheets, okay? Because gold is a metal and it's very malleable. Just by looking at these gold foil sheets, it reminds me of the gold foil experiment that Ernest Rutherford conducted in order to discover the nucleus of an atom, okay? Maybe it's just my chemistry brain that sees that and instinctively remembers that, okay? Let's talk about ductility. Metals are ductile. Ductility is the ability to be pulled or stretched into wires. So how can metals, or why are metals ductile? Metals can be pulled into wires because the sea of electrons allows metallic atoms to be stretched without breaking its structure. It's almost the same exact answers to why metals are malleable and we can hammer them into sheets. The sea of electrons allow them to actually change the shape, okay, without breaking the structure. That is why we can stretch copper into wire. Not only is copper a good conductor of electricity, it's actually ductile and we can actually stretch it into a wire, okay? So on the top right-hand side and the bottom left-hand side, we're able to see real-life examples of how copper is able to be stretched into wire. It's ductility. You can also see on the bottom right-hand side your traditional American backyard fence, okay? At least if it's not wooden. So we're able to pull or stretch this metal into wires, and it's very convenient, okay? We're able to use the ductility of metals and use it for our convenience as a human civilization, okay? So, in summary, metals lose valence electrons to form cations. Metal cations become surrounded by a sea of electrons. These sea of electrons are highly free, mobile, and delocalized. The nature of metallic bonding gives metals unique properties such as thermal and electrical conductivity, malleability, and ductility. So, now that you've had the lesson, now that you've had the lecture, please complete the remainder of your worksheet on metallic bonding and properties. When you are finished, please watch the YouTube videos posted with this assignment in Google Classroom. So, I hope you've learned something, and please complete your assignment. Thank you very much.